All right. Good morning, everyone. So last class we were talking about that extra credit assignments. So I do not, again, it is extra credit assignment. You don't have to do it if you don't want to, but just so I have some idea of like, who perhaps was able to watch the recordings, get some idea of the CRD, especially if that's something that you were not familiar with before. At least here in Athens, that I can see people more easily. Anyone saw the recordings at this point? Okay, so Tarishma, so not too many people. All right, so I'm asking that mostly because we're gonna start talking about RCBD in more depth today. And so, if you are not familiar with CRD, I highly recommend that you do go back and watch those recordings so you understand how, so a completely randomized design is what would be the simplest design, right? As we already talked about in the first lecture of experimentation. And then when we have some limitation on our experimental material, like for example, lack of homogeneity to fit all of our experimental units, then we go with something more complex, and RCBD is the first next step at that stage. And that's what we're going to be talking about today, first in the lecture, and then we're going to have an exercise about that. So we're going to first go ahead and do that lecture. So if you go on the course website, it's going to be the one for today's class. So on January 30th, you can just go ahead and open that. Before I get started with this specifically, anyone has any questions or maybe you need some clarification from what we talked about last class?
Roberto,
Yes.
will you recommend like any specific number of replicates, let's say a number of blocks per year, so we don't repeat the experiment the following year, or is it like because the standard is between 3, 4, taking into account that we have limited resources, but in case we just want to repeat the experiment this year, so there should be like any specific number of replicates?
Yeah, so that's a great question. Thanks, Selvin. So normally, I mean, as you alluded in your question, the default, or at least what you see most of the time, is ranging from 3 to 4 blocks or reps. That's very common. Really, something that we're not going to see in this class, but I can provide resources if anyone is interested, is to do this, I guess, in a more objective way, applied to your specific area. People would do a power analysis where you take into account what level of statistical difference you're trying to find between your treatments, what type of variability you're expected to find in the treatment response, and a few other things that go into a power analysis that really gives you a more exact number of reps. What happens, at least with my experience in my area, which is like field research with fertilizer mostly, is that you may do a power analysis that's going to say, hey, you need 10 blocks. But then it's going to come down to, can you really do 10 blocks? And I think that's why 3 to 4 has been this like happy medium of being enough, perhaps not what should be to be the best results, but it's a happy medium that is very acceptable for publishing, right? I mean, you're never going to get comments on a negative way from a reviewer because you have too many reps, but it would definitely get if you have too few. So like if you have just 2 reps, that's a little bit more risky, and I wouldn't really recommend going that way. But I guess something else that is also part of your question that I just want to make clear for everyone. So Sevin was asking about the number of reps or blocks and how that would impact your study on the following year, right? And I'm not sure, Sevin, if I fully got where you were going with that comment, but I just want to make the point that at least with field research, you're going to need a minimum of 2 years of field site data to be able to publish, right? So if you have just one site, you're going to still have to have at least 2 years of data on that site. Some journals require even for you to have 2 sites and 2 years on both sites, so a total of 4 studies to publish. And I mean, other journals, they may be specifically tailored for cases where you only have one site in 1 year, and that data is limited, and that journal addresses that directly. And so I think that generally you would want to repeat a study at least 2 years in one site, with the same number of applications, the same number of blocks. Unless you ran the first year and you notice, you know what, I did 10 reps and I noticed that, I could have gone with 5 or 4. Maybe it's okay for you to reduce if you go overboard and then you see you have too much or you have more than needed. But still you would have to have a minimum of 3 to 4 to be able to publish. So that's what I would say around that.
Yeah, Dr. Vaz.
Yes, Swabir. I think you're muted.
Can you hear me now?
Yes.
Okay, so talking about repeating the research on the stem field for, let's say, 2 to 4 years. What if it's part of your objective to assess treatments, differently, like you don't want any additive effect, like can you do it maybe on different field in the same site?
So you mean like you're still in the same overall location, but you're just changing the study from like the right side of the field to the left side of the field or something like that?
Yeah, maybe the two fields are, let's say, maybe 1 kilometer apart, maybe in a research station.
Yeah, I think it will depend on what type of research you're doing. Sometimes you may have carryover effects that you may or may not want to have in as part of your study, right? So for example, studies that are looking to soil health and applying like biochar or maybe another carbon amendment, you apply the first year and you do want to see the effect of that over time. So you have to be on the same land to be able to see that, right? On the other hand, perhaps you don't want to have that confounding effect coming from a previous year to the next year, and then it would make sense for you to move around to make sure you're getting a fresh piece of land every year, right? So it also depends on your objectives, but even so, let's say, even if you would have like two studies, let's say in 1 year in the same site, so very similar environmental conditions of soil and weather, that would still be just 1 year, right? And most journals are like to see at least 2. So you would still have to replicate that in time as well. I don't know if did that address your question?
Yes.
Okay. Awesome. Great questions. Yeah. So the last year when I taught this course, we did not. So as we're going to see, we're going to be talking about randomized complete block design. Then we talk about split plots, but all within the context of 1 year. We didn't really go through analysis of multi-site year experiments. If this is something that you're interested, we can try to fit into the schedule as well and go through an exercise like that. There is a little bit of a difference between analyzing 1 year worth of data versus 2 or 3 or 4 years of data that are the same design, right? So let's say if your objectives is to take this study and then replicate in 3 sites and then 3 years, and you want to analyze all that together, there's a different way that we need to run a model to accommodate for that. So we can talk about that if people are interested. You can let me know later. Awesome. Thanks for the questions. Anyone else has any question before we get started? All right. So, as I like to tell you that I really enjoy when you're asking questions and show me that you are thinking about it and not just looking at a screen. So I do encourage you, if you do have questions, continue to feel free to ask them even during the presentation. That brings great discussions, and I'm sure everyone can learn from everyone else's questions. All right. So again, today, randomized complete block design. We talked a little bit about this design in comparison to a completely randomized design last time. Today, we're really going to narrow on RCBD and trying to understand, again, when we use it, how is it working behind the scenes? What's the ANOVA table look like for this type of design and other things? And then we'll get into the exercise. All right, so today's goals are to explore key concepts in randomized complete block design. So we're going to revisit again this concept of heterogeneous experimental material. That's the driver of you needing to use this design. We're going to talk about treatment randomization, the effects model. So we're going to look into how the model looks like and how that model translates into an ANOVA table. And that's going to be it. All right, so we're going to keep up with our motivation example that we were using before. So we have a two-way factorial where we're analyzing the effect of nitrogen fertilizer rates, and we picked three rates, 0, 100, and 200 kilos of nitrogen per hectare, and the effect of potassium fertilizer rates, so 0, 30, and 60 kilograms of potassium per hectare. And again, because we're interested not just on the main effects of those two factors, but also on their interaction, that means we have to have all 3x3 combinations of these different levels of nitrogen and potassium. And again, right, so on the previous lecture, we talked about once you determine how many treatments you have, how many blocks or wraps you're going to have, and you make one times the other, and you get the total number of experimental units you're going to have. And if you do know, what is the size of your plot, let's say I know my plot's going to be at least 4 rows and at least 30 feet long. You have an idea of the area you need, and then you call your farm manager and you say, hey, do you have 1 acre within homogeneous soil for me to run a trial? They may say yes, but if they come back and say, hey, I have about half an acre in a soil type and another half acre in another soil type, they're right next to each other, do you think that would work? It would work if we use the proper design, right? So if you do have heterogeneous material like this, where our soil is different, we would need to use something like RCBD. And again, this example here is field research, but I want you to be thinking about all sorts of different sources of variability that you can include in your study that are not part of a treatment design, and you can accommodate that with RCBD. So, in food science, perhaps you have an incubator that only fits a certain amount of plates, and then you have many more times than what fits into one incubator. Maybe the incubator can be a block, or maybe the person that is running the analysis. Perhaps there is variability between me doing something and you doing something, and so you want to say, you know what, Leo is going to be a block, I'm going to be a block, and then other person is going to be a block, and we're going to block by person. So that variability from person that you really don't care about, you just want to control for it, becomes the block. Or perhaps, I think we talked about last class with one question that Charles asked, perhaps you cannot do everything in a day in the lab, and you have to split that across multiple days. Well, then day can be your block, and then you just have that effect, so that variability from day to day confined to your block effects. Other examples, again, if you're in a greenhouse, for example, if you work in a greenhouse, you know that there is a gradient of temperature and humidity from where the fan is to the other side of the greenhouse. So maybe you want to block, let's see, perpendicular, right? So if the flow is going in this direction, you want to have your blocks on this direction, because then they're receiving a similar, well, the blocks are receiving different levels of temperature and humidity, but you're controlling by that, having your blocks in the right direction. So all sorts of things that you can think of. I know there's variability around here from whatever source, and that variability may impact the response variable that I'm measuring. You can block by that variability. And as long as you can think of that before you do the study, then you can randomize according to a block design and have that extra variability still there, but you can separate it from your treatment effects. So in our case here, so we have our variability in soil type. We're going to do a randomized complete block design as we saw previously. So if you remember, and we mentioned this last time, the difference here between an RCBD and a CRD is that on an RCBD, a randomized complete block design, the randomization of a treatment to experimental unit is restricted. There is one restriction in randomization. There are 0 restrictions in randomization in a CRD. So CRD, simplest design, no restriction in randomization. RCBD, 1 level of complexity up from a CRD. RCBD, we have 1 level of restriction when we randomize our treatments. And as we already talked about this, for your design to be an RCBD, you have to have each treatment appearing at least once in each block, right? So if we come back here to our example of perhaps a person being a block in a lab study. So let's say you have 9 treatments, and then I say, you know what, Leo is really good at doing whatever step of this analysis, of this lab analysis, that like titrating something, or maybe mixing some or some chemical, making some chemical reactions, whatever it is. Like Leo is really good at that, so maybe he's going to do that. And I'm just going to focus on what I am good, which is another step on that process. And if all those steps are being applied to all of your experimental units, that is not really a block, right? You're not doing the right way, because then let's say for some reason I'm doing something really well with some of the treatments and then not so well with other treatments. I am having an effect on the treatment effect differently. I guess I'm just making myself more confused. So let's just move on. But I guess I wanted to keep in mind that a block, for a block to be a block, it has to have all treatment levels within that block. That's what makes a complete block. And because of that, the way that we ensure that that happens is by randomizing each block individually, right? So let's say in our example, we have 9 treatments. I have 9 plots per block. You go there, you take your hat with all, the little papers with the number of your treatments, and you say, okay, plot number 1 on block 1 is gonna get treatment X. Plot number 2 on block 1 is gonna get treatment Y, and so on. And then once you randomize all those 9 treatments to the 9 plots on the first block, you do the same thing separately, individually for block 2, and then 3, and then 4. We're going to do this again using a computer, so we're not going to be drawing paper pieces from a hat, but I guess that's the idea. So in our example here, we have 4 reps, and then the total number of experimental units, which translates to total number of observations, are going to be 36. We already saw this, but just to recap, so by knowing we have a limitation beforehand and by planning accordingly and having an RCBD, this is how that randomization will look. I mean, this is one potential randomization on this study, where I'm just highlighting here treatment 1 for us to keep track of. As you can see, treatment 1 is appearing once in each block, and not more than that, not less than that, where each column here is a block. And you can see that blocks are fully contained within a given soil type, right? What you do not want to do, so the example I was giving you, that if you block in the wrong way, as far as in this example here, would be if you have blocks going on the east-west direction rather than south-north. Because if you have east-west, if a block is going this direction, then you still have treatments, some treatments falling in good soil, some treatments falling in bad soil, at least in this example. And then it just confounds again everything, right? So you do not have the power of separating those effects of, in this case, soil type and treatment. I think somebody had their hand up.
Yeah, Dr. Vesas, I had one question. So if we know that our plot has a topographical difference, I mean one side is a little bit high and one side is low, and I'm randomly assigning my treatment, and will it consider as a bias if I intentionally put one treatment at the top side, for example, treatment 1, I'm putting it in the top side of the plot, and for the next block, I'm applying it in the like lower side of the plot, because I cannot just randomly assign both of treatment 1 to the top side. Is my question is clear? I'm not sure. Did you understand my question?
I think I'll try to answer, and if I didn't get it right, you can help me understand again. But so let's say, so is that Ariful?
Yes, yes, Dr.
Ariful, thanks for the question. So the first thing I would think is that variability source, in this case here, elevation differences, do you think that can have an impact on your response variable?
Yes, because yeah.
Yeah, so if you think it does, which I believe most of the time on field research, if that gradient of elevation is significant enough, it will most likely have differences in water movement and nutrient movement, which those things are important for crop growth and development and yield. So, of course, everything is going to have some slope. Is going to be more up to you to think, okay, is this gradient and slope in this field enough for water to really be able to move and move nutrients around? it would be the same case as here, right? So imagine that instead of having soil type, if you have elevation. So let's say that the darker soil is actually your like your higher elevation soil or higher elevation part of the field, and then the sandy here would be your lower elevation part of the field. If you are, let's say, if you're not blocking on the correct direction, like we are showing here, if you're blocking on the, well, if you're not blocking at all, or even if you're blocking in the wrong direction, which is even worse, then that could be an issue. Yeah. So just to give you an example, in our studies in my team, we work a lot with nitrogen. So I call, we call a farm manager and say, hey, do you have this extra space in the farm for us to run a trial? They say, yeah. And then I ask them to send me a pin, like a GPS coordinate pin of the field that they identified. And then with that pin, we download open source data for Surgo, soils data, and elevation as well. So we have an idea of that variability, and that's still all in the planning phase of the study, right? We have not implemented anything yet. And then we use that information to say, you know what, I see there is a gradient in the east-west direction, so let's block to accommodate that variability. Or maybe I see there are different soil types there. So even before we go out and pull soil samples, we may still have some idea from Surgo of, if we have variability in that field as far as soil types, and then we block accordingly. So I would, yeah, if you do have an elevation gradient that you think it's enough to move your treatments around and impact your response variable, ideally you would block by that. So you have a full block within one level of that gradient and not one block across all levels. Did that help?
Yes, thank you, Dr. Vistas.
I'm careful. Yes, Comfort.
So does it mean that sometimes we are not randomizing, like giving it a chance, because sometimes we have to really position the treatments even in a block so that maybe they are not staying close to each other. So is that still like something happening by chance? Is it true randomization, or we say structured randomization?
So, well, with the RCBD, we do have that structure randomization, right? Which is what we're seeing here. So within each block, we're randomizing completely independently from the other block. However, our assumption is that within a block, the conditions are homogeneous. It's okay if those conditions are heterogeneous from one block to the next, but within a given block, we're trying to accommodate that block in a way that conditions are homogeneous within that block. So we wouldn't really, so if you have a block, if by random chance all of your treatment ones end up on the south side of this plot, of this map, I mean, you can rearrange things if you want to make it a little bit more spread out, but if you're blocking on the right direction and you're doing, randomization of the treatments to the experimental units, you should be safeguarded, because you are assuming that within a block you have homogeneous conditions and you're randomizing within the block. Did that answer your question?
Yes, thank you.
All right. Well, thanks for the questions. All right, so just coming back to our lecture here. So, the treatment one and its replicates are highlighted. So again, you see differently from the CRD, where the CRD, we do not have blocks, right? We do have replication, but they're not as structured in blocks. So on a CRD, which is the simpler design, you could end up that you have two treatment ones or even three treatment ones right next to each other because you have no limitation on that randomization. In RCBD, we have that limitation being by block, and so now you see that treatment one is appearing once in every block, not more, not less than that. And again, because our assumption here is that experimental material is heterogeneous, and we are safeguarding our statistical power when we're estimating treatment means and performing comparisons. So we should be good here. We're doing what we need to make sure that we can separate our treatment effects from the block effects. So the block, again, is not to eliminate. So the variability is still there, and we're just handling it in a way that we can separate the effect from the block from the effect of the treatments and still be able to do treatment comparisons that are fair. All right, so let's look into some formula here. You know, I don't know how familiar you are looking at statistical formulas. We're gonna start looking into these to have a better idea, because if you understand the formula, then becomes a lot easier to understand what goes into your ANOVA table and what effects are present there. So this is the model for is the model for RCBD, where your Yijk is going to be one observation. Maybe we can think of yield. So it's going to be one yield data point coming from the kth block. So this is the block effect. From the ith nitrogen rate, so that would be the alpha I, and the jth K rate, which is going to be your beta J. Notice we also have here, well, I guess I'm just going to click on the slide and we'll talk one by one. So mu is your overall mean. So the overall mean of the entire study is represented by mu. Your, I don't know how to pronounce that actually. What is that? How to say that symbol?
That's rho.
Rho, thank you. So rho K is that, I was going to say P, so thanks for helping me not make that mistake. So rho K is that differential effect of the kth block, right? So all the block effects are going to be confined to this term here. Your alpha I is going to be a differential effect of the nitrogen rate. So let's say we have 3 nitrogen rates, so we have 3 I's. So going from 1 to 3. I goes from 1 to 3. K here, because we have 4 blocks, just goes from 1 to 4. And also J is our effect on potassium. So we have 3 levels. J goes from 1 to 3 as well. So our beta J's are going to be the differential effect of the Jth potassium rate. We have this interaction term, alpha beta IJ. That's going to be the differential effect of the combination of a given nitrogen rate and a given potassium rate, because we are interested in that interaction. So this term has to be in our model. And then we have our error term, our EIJK, which is just the residual corresponding to the block K of N rate I and K rate J. So this is a very typical, this is how you would write out this model. And it's interesting for us to look into this, because this is going to be connected to your ANOVA table, which is going to be one of the ways that we're going to see if we're running the correct analysis or not, is by looking at your ANOVA table, which comes directly from the model that we type in R. So being able to understand this model and what components it has, it's going to connect directly with the model in R and with the ANOVA table that we expect out of that. All right, so I'm going to show you an ANOVA table for our study specifically. And I just want to tell you that N is the number of levels in nitrogen rate. So it's going to be equals to 3. K is the number of levels in potassium rate. So that equals to 3 as well. R is the number of blocks. So we have 4 blocks. And uppercase N is the total number of observations or experimental units, which is 36. One thing I just want to quickly make a mention here to you is, remember we talked about experimental unit and observational units. We have 36 experimental units that were randomly assigned to a treatment and therefore are independent. This is a big assumption of the ANOVA, and the way that we check, or at least that we come in with that assumption into a study, is the fact that you randomly assign treatments to plots. So we have 36 degrees of freedom. We have 36 pieces of information coming from this data set that we're going to break down to estimate all those parameters in the model that I just showed you. What happens is, let's say if you do subsampling and you don't, well, again, there's a modeling way of taking care of subsampling, and there's a easier way of just taking the average. So let's say if you take our six plants that we're doing yield, we just take the average of those 6 plants and represent as one value. But let's say for some reason you're measuring how much yield you have on a plant basis, and then you have 6 observations per plot. Then you basically have 36 times 6 would be your total number of observations. That is not correct, because it's breaking your assumption of independence. Those 6 plants within a given plot are not independents because they receive one realization of the randomization process, and therefore they break this assumption of independence. So that is one of the pillars of experimental design, is that assumption of independence being there and us making sure that we are following it. Oh, no, this should not show up like that, actually. Let me see if I just keep moving, if that, okay. So I think something happened when I was rendering this, this slide here that it was not supposed to show the code in just the table, but as you've seen, it is showing the code and not showing the table as a result of that. Oh, that's a bummer. Yeah, I'm gonna have to work on this to fix it and then send you a version that does not show the code and does show the table afterwards. I'll share that with you afterwards. But basically, to not leave you completely unaware of what we would talk about. So an ANOVA table is going to be first something that I would recommend you do this even before you implement your study. The reason for that is when you understand your ANOVA table, if you're making mistakes, it's better to know a mistake on the planning side so you can fix it when you implement it. But on an ANOVA table, you're always going to have a column with your sources of variation, which are basically going to be related to this model. So we're going to have a source of variation for block, one for the effect of nitrogen, one for the effect of potassium, and one for the interaction. And then finally, we're going to have an error term as well. Yeah, I guess we're going to have to come back to this and revisit this at a later, maybe next class, or maybe I'll send you this updated version, later today when I get back to the office, and then we can revisit this concept again. But I do want to come back to this and walk you through this table once I fix it, because it's really key for us to understand a few components of that ANOVA table, especially the distribution of degrees of freedom, and how that happens in a randomized complete block design, and especially how is that different from a CRD, which is a very subtle yet important difference from a CRD. Yeah. ETH on the question? What do you mean? Oh, the equation. Okay, yeah. So EIJK is the residual. Oh, it just means the ith. So it's like so I is the index, right? So I would go from 1 to 3 in our case. So ith is just meaning like the first, second, or third position. Yeah. So the TH is just like first, second, that superscript, I guess. Yeah, even though here is not in the superscript format, but that's what it means. Yeah. All right. Well, yes.
So I can see the ANOVA table, the PDF that I downloaded, so I can share my screen if you want to show it to everyone. Or
let's see. Okay, yeah, okay. I think I can see that here as well once I turn that into a PDF. Nice. Thanks, Shakir. That's really helpful. All right, so ideally you would not be seeing the code behind it that I used to create this table, because that's really not important here. We would focus on the table itself. All right, so perfect. Thanks, Shakir. All right, so we have here our sources of variation, and notice how they match what we had in our model. So we have a first line here for block, but then we have nitrogen rate, potassium rate, the interaction, and that error, which is our EIJK. It's all error. Here it's called error, but it can also be called residual. And this is going to be important for us as well as we move forward with this analysis. And then we have the total. What I want you to notice is that your total number of degrees of freedom is always going to be your number of observations minus 1. So here, if we start from the bottom here, that means we have 35 degrees of freedom that we can use to estimate the other model parameters coming from the error, the interaction, potassium rate, nitrogen rate, and block. So this is our total number of degrees of freedom. And basically this concept here, if you've never heard or not familiar with degree of freedom, you basically get 1 degree of freedom for each data point that is a fully independent data point from that plot. Meaning, if you have your experimental unit, there's going to be 1 data point for 1 degree of freedom coming from each experimental unit. If you do subsampling, then you would make, so let's say again, if you take 2 measures of yield per plot and you have 36 times 2, that is subsampling. And that the danger of that is if you don't properly specify you have subsampling in that design, then you get inflated number of degrees of freedom when you should not, right? This is number of observations that were assigned independently to a plot, and they just have 1 per plot. Even if you have more data points, that should be either averaged before you do the analysis or taken care of in other ways that we're not going to be exploring here. All right, so we know we have 35 pieces of information to play with here. Let's see how we're distributing that in degrees of freedom here in our ANOVA table. So we're always going to do the number of levels minus 1. So we know for block, we have 4 blocks. Minus 1, we get 3 degrees of freedom to estimate the effect of block. So we from those 35, we consume 3 for block. Same for nitrogen rate. We do number of levels minus 1. We have 3 levels of nitrogen rate minus 1. That equals 2 degrees of freedom required to estimate the nitrogen rate effect. Same on the potassium rate. We get 2 degrees of freedom. For the interaction is basically multiplying the number you have on each one of those individual lines. So we have 3 minus 1 coming from nitrogen rate times 3 minus 1 coming from potassium rate. We need to consume a total of 4 degrees of freedom to estimate that interaction effect. And then we have our error. And our error here is basically, I mean, the formula is more complex, but I guess what I want you to see is that we have 24 degrees of freedom in the error. So it's basically the remaining from what we used for our treatment effects and experimental design variables minus the total. That ends up being 24 degrees of freedom in your error. All right, so we know how many degrees of freedom we're taking up for each one of those levels. Then we calculate the sum of the squares for each one of those lines in the ANOVA table. You can think of sum of the square of just being a way of you assessing. I'm not showing you here the full formula. If this is the first time you're seeing this, I do recommend you go back to an intro to experimental design class and really learn more about this. Again, this class here, just to bring these concepts back to you, but it's not to start from 0. So here I'm summarizing that and just giving you an idea of your sum of the squares for each one of these variables is basically how much variability there is being explained by each one of those effects. So there's some variability explained by block, some by nitrogen, some by potassium, some by the interaction, and then everything else that is not explained by those end up in your error variability. The way that we would go down this table here, normally when you ask for an ANOVA table, the ANOVA table itself, even in software, is doing all these calculations behind the scenes, but normally we would be looking to a column for source of variation and then a p-value. That's what we're really after. But all of these are steps that happen in between until you get to that p-value. So sum of the squares is basically assigning how much variability you have. Then we calculate the mean squares for each one of your effects here. So the mean square of that effect, specific effect, is basically the sum of the squares of that effect. So let's say for nitrogen here, the mean square for nitrogen is going to be that sum of the squares for nitrogen divided by degrees of freedom for nitrogen. So it's basically taking this value and dividing that by 2 in this case. This is your mean square for nitrogen. We have 1 for potassium. We have 1 for the interaction between nitrogen and potassium. And finally, we have a mean square for your error. Once you have the mean square for each one of those levels, then we calculate a NAF ratio, which is basically just the effect, the mean square of that effect that you're interested. So we're interested here in nitrogen, potassium, and interaction, divided by the mean square of the error. Normally, this ratio here, we want it to be after you divide this and you get the result of the F ratio, the larger it is, this number, the stronger effect you have for that specific line on your ANOVA table. one thing I want you to notice here is that this error, or the mean square of the error term, this MSE here, is what we're using to test the significance of our interaction, is what we're using to test significance of potassium rate and nitrogen rate as well. So ideally, what we would have is you have a lot of treatment effects. So if you tested, let's say, nitrogen rates, you would want to see a lot of variability being explained by nitrogen, which would fall under your sum of the squares for nitrogen. Your degrees of freedom of nitrogen are really fixed because they depend on how many levels you have, how many levels of nitrogen you decided to have. So the two ways to make sure you find statistical differences in any model, and this is one example, is to have a lot of variability falling in that level. So you have a large treatment effect that will be represented by the sum of the squares of nitrogen, and by having a very, let's see. Let me make sure I don't confuse you on my thinking here. So the error, we wanted to have more degrees of freedom here, so MSE is smaller. Yeah. So we wanted this MSE, which is on the denominator of this equation for all of these effects, to be small. We want small variability in your error. There are two ways we can do that, just mathematically thinking, right? So one way is to really have very small, very little variability being explained by our model. What does that even mean? So let's say you do a study, let's say that you should have blocked, but you didn't. Now you have all this extra variability that is not being explained by nitrogen itself or potassium itself or the interaction, because you have this noise between, oh, I have some treatments of nitrogen that all fell into good soil, but really they're the zero nitrogen. They should be low yielding, but they're high yielding because they fell in good soil. And then we have some treatments that apply more nitrogen. I was expecting to have a higher yield, but they mostly fell in bad soil. So now my zero nitrogen, my 100 nitrogen are very similar, not because of the treatment effect, but because there's extra noise that I cannot separate. That would make your sum of the squares of error to be higher. So we have a larger error. We don't want that, right? We want our error to be small. That's why we control things. That's why we try to be very careful when we're conducting studies, right? To make sure that we're always pulling samples, let's say, from the middle two rows. We don't have variability here of some people taking from the outer row, some people taking from the middle row. That we always, so everything that you think of in experimentation that you're doing carefully is because we want to reduce the chances of having this error inflated. That is all to keep things consistent, decreasing the amount of information that goes into your error. Another way here to also make sure that your mean square of error is small is by having a large degrees of freedom of the error. And I want you to pay attention here because this is the key concept and one of the key differences between designs. Our error, the degree of freedom of the error is 24, okay? So this number here is 24. Why do you get higher chances of finding treatment differences if you increase replication? Is because basically you increase your number of degrees of freedom that go into your error. So imagine we have the same design, but instead of having 4 reps, I have 10. Where that would play a role is basically everywhere in this formula of the degrees of freedom of the error, where I have R, instead of R being 4, it would basically be 10. I would have a lot more, well, I would have a total number of observations that would be larger because now I have more blocks, right? So I have more plots, more degrees of freedom total. But notice that if I increase from 4 to 10 blocks, I'm still only consuming, well, I'm going to consume more on the block effect, but I'm just consuming 2 for nitrogen, still just consuming 2 for potassium, and still just consuming 4 degrees of freedom for the interaction. So the treatment design is not consuming more degrees of freedom just because you increase reps. So making you have more degrees of freedom on your error, which is great. So every time you think, if I have more replications, I'm going to have more chance of finding treatment differences. This is why. It's because you're going to end up with more degrees of freedom on your error, which makes your MSE smaller, MSE of the error smaller, which means that when you make this division here, your F ratio is going to be larger for your treatment effects. This is how that's connected. And this is how it's so important for you to really check your degrees of freedom of your ANOVA table especially of the denominator, to make sure that you were able to write in code the design that you did on the field. If this is the first time you're seeing this, it may be too simplistic for you to fully understand. If this is not the first time, I hope that this was a good review for you to remember some of these concepts. Yes, Comfort.
Yeah, so are you saying that we need more degree of freedom for the hero? Like, should our project support having higher degrees of freedom so that in the long run we can have lower MSE?
Yeah, so again, to have lower MSE, you either decrease the amount of external variability that is being added that is not related to your treatments, and that decreases your SSE, or you increase the number or you increase the number of replications, which has an effect on the degrees of freedom of the error, which makes your study more precise, right? So sorry, your question was if over time we should increase number of reps?
I think you already explained what
Okay.
I wanted to. Thank you.
Thanks, Comfort. Yeah, and this is always going to be, so why don't we do more blocks? Why don't we do more reps? It's always going to fall down to some type of limitation. Maybe you don't have enough funds to cover more area, to buy more fertilizer, to buy more seeds, or to harvest those plots. Maybe you just don't have space in the farm. Maybe the farm has only 1 acre, and for you to have 2 times the reps, you have to have 2 times the size of the study. So it normally falls into some type of limitation, right? And so again, having the 3 to 4 is perhaps conventional. You see that most of the time, at least in the literature that I'm involved with. Perhaps in your fields it may be different. So let me ask here. Does anyone in the class work in a field where number of reps or blocks is not particularly 3 or 4, perhaps is just 2, perhaps it's 10, 20. Anyone have any thoughts around that? Okay. Yeah, so it seems like with the class, we're pretty standardized with using 3 to 4, perhaps 5 blocks in our studies or replications in our studies. Something else I want to tell you here, which is really interesting. So we just mentioned that having more degrees of freedom on the error is better, right? That's going to give you more power to find statistical differences of your actual treatment effects, which is what you're really doing this for, right? We're doing this study because we're interested in our treatment effect or the effect of our treatment design on the response variable. So I want to pose you a situation here. If you did not watch the CRD lecture, or maybe if you're not familiar with it, I'm going to give you one spoiler here that one of the differences in the model and therefore on the ANOVA table between a CRD and a RCBD, so we're looking at RCBD right here, is the block effect. Since you do not have blocks in a CRD, you just don't have this term here on your ANOVA table for a CRD. Meaning that if you don't have this term, these 3 degrees of freedom that right now we're consuming for block would actually just end up back on your error. So we would have 27 degrees of freedom on the error on the CRD on the same data set. Then you may think, well, isn't that better? Why don't we just use CRD then? Because we have more degrees of freedom on the error, therefore we have more power to find statistical differences. Well, the problem is if you need an RCBD and you run a CRD instead, you're going to have you're potentially going to have so much more variability on the sum of the squares of the error that even by increasing your degrees of freedom by 3 is not going to help you with that. Plus, you don't have any lines on this ANOVA table that will fully capture that variability in this case of soil type. We have that. Block is doing that for us. And we're going to see an example in code later of how this plays out. Now, you may ask me, I think maybe even somebody truly asked this in the past. So if you should have run an RCBD, so you have variability, have heterogeneity, should have done RCBD, and you do a CRD. Well, you most likely going to have inflated air, and you're not going to be able to separate the effect of, in this case, soil from treatment. They're together. There's nothing here to help you separate. You're probably not going to find too many statistical differences in your design, even if you're expecting to, because your area is so large because of that confounding effect of the soil. That is just, everything is very variable. Like you look into your replication yield, the yield value for replications of a given treatment, they're all over the place. So that is the worst condition. If you need an RCBD and you do a CRD instead, you're really bound to that data. There's nothing you can do about it. You're just gonna have to repeat this study again and do a better design next time. Now, what if I ran an RCBD and then I go through my analysis and then my block effect is non-significant? That is telling you, you know what, for this field here, maybe you didn't need to block. Maybe you could have done an RCBD. However, it's better to do that, to run an RCBD with the best information you have, blocking in the right direction, coming back and having in your model that you're saying your block effect is not significant, you don't need your block. Maybe next time you can do a CRD, which then is going to be good for you because you move these 3 degrees of freedom that right now are going to block. They're going to fall into the error for next year's analysis. One thing I want to make clear, that at least this is the way that I've been trained and the way that I operate. This design, then this perhaps is one of the main differences between experimental design and machine learning. Experimental design, you have your model set even before you collect data, because this model is coming from your experimental design, your block effect, and from your treatment design. And this model is set because you plan for it, you apply things in a block, you apply your treatments, and so on. So in experimental design, there's not as much room for you to play around with your model. For example, oh, I ran RCBD, my block effect came non-significant. I'm just going to remove it from my model and run as if it were a CRD. Some people do it. I guess some people they have a way of justifying that. I particularly don't do that, because if you ran an RCBD, you have the block effect. It means you did randomize, you did have that restriction of the block on randomization. Even if it comes back as non-significant, you still did that. That's still what happened on the field. So I don't play with the model from an experimental design. Yes.
So if you run an RCBD and you don't necessarily need to in your block that's not significant, does that impact the sensitivity of your model in terms of significance even for the other treatments?
Okay, that's a great question, right? So Jonathan's asking here, if we ran an RCBD and we didn't need to because the block effect came non-significant, right? That means that next year you could run a CRD, but this year already ran this. And if you had run this study as a CRD instead, you would have gained a little bit more power because you would dedicate these 3 degrees of freedom back to your error, right? So if you run RCBD and block comes back as non-significant, that it means you could have been more powerful if you had done a CRD, which is the best situation is you run an RCBD and then your block comes significant because you blocked appropriately. I mean, I guess it's not the best in the sense of I want my block to be significant. It just means that you did the right decision when you plan the study, right? Now, if you run RCBD and block comes back non-significant, it means you could have done a CRD, so you could have gotten a little bit more power on your error, but it's still okay. It's still, you can still separate, your treatment effects are going to be clear. You're not going to be penalized as much on that. The worst condition is if you needed an RCBD and you actually ran, so you needed to have blocks and you did not use blocks. That's the worst because there's nothing you can do to separate those effects, right? Swabir.
Okay. So does that mean that when you don't have treatment or maybe significant effect in your block using RCBD, it means you've used the wrong design, if I understand what you're saying?
Yes, it means that you could have done a CRD in this case. Yeah.
So the block must be significant for RCBD.
Yeah, I mean, so if the block is significant, it means that you did the right planning for the condition that you have, right? Sometimes it could be that you believe maybe there's some variability source there that you're trying to accommodate, but maybe that variability source, maybe it was there, but it was just not severe enough to make your block significant. So again, if you do an RCBD and block comes non-significant, it means next year you can do a CRD. And you can basically not consume 3 degrees of freedom for block, and those go back to your error. You have a little bit more power to find statistical differences on your study. Yes, Ashbin.
Dr. Bastos. If the experiment doesn't have the more than suppose the experiment has only one replication, is there any way we can analyze this data, and is it valid experiment? What do you say?
If you just have one replication, I don't think you really have an experiment, because so the whole idea is that really the minimum number of replications required for you to have a study is 2. And the reason for that is because there is no way you can calculate error around one value, right? You need at least 2 values to calculate a standard deviation around any value. But then, yeah, so if you just have one replication, you have a demo study, like a demonstration study, I guess. You don't really have a like experimental design study.
Thank you.
Following that same question, so what if you have like a very high level of, like, let's say we have 4 factors,
Mhm.
sometimes I would say, even though we don't have replicates, people will just take the higher level factors, like ABC, for example, they will take it as an estimate of the error, they will estimate the error based on the sum square of interactions.
Right.
So sometimes I would say that, but I don't know if that's something for everybody.
Yeah, so Charles here was asking, like, what if you have multiple factor levels and then people analyze that as different ways of how one factor is related to another and use that relationship as to establish an error. So there are some designs, especially in breeding, that use partial factorial designs that, or I mean, there are many types of designs that perhaps can be connected to what you're saying. We are not going to go through them here because they're very specific to certain areas. Also, I don't use them on a daily basis. I've learned about them, but I haven't really used myself to be able to teach you from experience. But those, yeah, so let's say, for example, if you have, and we're going to see this when we do the split plot. It's actually going to be really interesting for you to think about. So if you have 4 treatment factors and they are nested, right? You're going to see that on the, so let's say we have a plot like that is larger, and then we have, and this plot, let's say, is nitrogen 0, that it received no nitrogen. That's the treatment for nitrogen. But then potassium is nested in nitrogen. So now we have on that big nitrogen 0 plot, we have 3 smaller plots for potassium that are randomized for each one with 1 potassium rate. This is basically one example of what a split plot will look like. So if you think about it, if that's what we have, so let's say we have 3 big plots for nitrogen, so nitrogen 0, 100, 200, and then with inside each one of the big nitrogen plots, we have 3 smaller potassium plots, right? So nitrogen is not replicated because I don't have 2 plots that are receiving 0 nitrogen. I just have 1 big plot with 0, 1 with 100, 1 with 200. But potassium is replicated inside nitrogen. So it's almost like nitrogen works as a block for potassium, which is actually what it does, right? So I guess that is related to what you're asking, right? But let's say if you just have, so let's say in our case, we have 9 treatments. If I just have 9 plots, 1 plot with each treatment, I really don't have replication, right? I don't have any treatment appearing more than once in that study. And then that's the problem, because then you cannot calculate errors around anything. Yeah. How are we doing online? Anyone has any questions? Right, great. And then just to wrap up this idea here, that at least my philosophy when I'm working with experimental design data is, okay, so let's say you could be tempted to say, okay, I did run an RCBD. So on the field, I have blocks, I randomize individually by each block and so on. I bring this data into R, I analyze it, my block effect is non-significant. I'm just gonna drop that block effect and treat this analysis as a CRD, even though on the field, I ran an RCBD. Again, I particularly do not promote that. I think that the model that you run is the model that represents what you did on the field. That's what we do in experimental analysis, which again is perhaps one of the main differences between experimental analysis and machine learning. Machine learning, we are gonna go crazy on models. We're gonna try different models. We're gonna try different parameters of the models. We're gonna really is a big party, right? We're gonna try every single model that we can. That is not the case in experimental design. All right, I think these concepts are gonna perhaps become a little bit more solid once we start analyzing the data in R. But for now, anyone has any more questions or thoughts? All right. I'm just trying to get to my last slide here and get a summary. So in a quick summary here, so RCBD is this design that we randomize with one restriction. In our case here, our restriction is soil type. And so each block is randomized separately. Each term of that effects model has a row in the ANOVA table. You're going to see this ANOVA table in R when we run that model. And so we're going to be able to really notice that all those rows of the ANOVA table that we saw here that are connected to the model are going to come back to the ANOVA table in R as well. When we include the block in the model, it does consume, in our case, 3 degrees of freedom from the error. However, in our case, because we had heterogeneous material and we applied a block, the amount of degrees of freedom we're consuming on the block has a lower impact based on how much variability we're allocating to block. So block is getting a very large amount of variability that is going to that block sum of squares. So even though we're consuming degrees of freedom, we're still gaining power because there's a lot of error that is going to the block that otherwise, if we did not block, it wouldn't go there. It would basically be mixed within our treatment effects. In a properly conducted RCBD, we would hope that the amount of that variability explained by block is relatively greater to the consequence compared to the consequence of consuming those degrees of freedom for the block that would otherwise would end up in the error term. So I guess this is basically a sentence summarizing what I said earlier. All right, so this is it for our lecture. So today we're going till 11:30. I think, well, before I say anything else, just want to make another quick empty space of silence if anyone has any questions. All right, so I'm gonna take a 5-minute break, and then once we come back from that break, we're gonna basically implement an RCBD analysis in R. You are expected to have already done all the steps we talked about last class, as far as having that project, having the code and data in the right place. I'm not gonna walk through that, so if you don't have that, make sure you do it during the break, because we're gonna get back and start coding straight up. All right, 5-minute break. All right, so our time for the break is up. So let's resume our activities here. So I forgot to mention initially, and this I guess is going to be more important for those here in Athens. So we have Dr. Jessica Barb in the room here today. She's a professor in our department, and she's been conducting teaching evaluations across all different courses. She is helping us out with improving our teaching, and so by providing feedback. And so she's here just observing me for the most part. So don't have to worry. No, well, she's not observing you. It's mostly just me and what I say and how I interact with you all. So that's why she's in the room. Thanks, Jessica. All right. Okay, so if you go to your 04 RCBD project, as you remember, always launch your R-related stuff by launching that project icon and not your script icon, just to make sure you have the proper relative paths in place. So if you launch that, if you come on the Files tab, if you're not seeing that yet, you come on the Files tab. If you're not seeing the main folder of the project, click on the R blue button. This always brings you to that main folder of this project. Go on code and launch that script that I shared with you, the RCBD partial. All right, so the goal of this exercise here is going to be for us to create an analytical workflow for a randomized complete block design analysis that goes from data import all the way to a publication ready plot and all the steps in between. If you are not seeing your outline yet, you can toggle on your outline button and see that outline. For now, I don't need it to click anywhere in the outline, but I just want you to look at the steps we're doing. And these steps, I think it's something that you're going to realize throughout this class is, again, every single analysis, regardless if it is experimental design, if it is machine learning, whatever it is, we're always going to follow a very similar structure. And I think that having a structure in place will help you to implement these things in your projects as well, because you do have this structure to help guide you what to do. So you can see that we're always setting up things, right? So we have a setup where we bring packages and import data. We're going to always do EDA, always do some exploratory data analysis, understand your data to see if you have maybe, some value in your data set that does not make sense, does not make biological sense, maybe have a typo. If you don't have EDA, you go straight into modeling, straight into ANOVA. You may get some weird results in your ANOVA, and you may not ever know why you got that. So always look into your data through EDA. You use tables, you use graphs. Normally, you're going to have some level of wrangling required. So I would say always I import data, I load my packages, I do EDA, I do wrangling, and then I do some modeling. In our case, it's going to be a experimental design type of analysis. It could be machine learning. So even if you change the type of analysis you're doing, this workflow is still consistent. You're going to run some type of model. You're going to check your model assumptions or the validity of your model. This is so important, and I don't think everyone fully appreciates the need for that. We need to check the validity of our model assumptions, and we'll talk about model assumptions when we get to that point. Once we check our model assumptions are met, then we use this model for inference. So then we extract means from the model, we do pairwise comparisons with this model, and combine all that into a final plot, like a final publication ready plot that incorporates different components of this analysis. All right, so here on the setup chunk, I believe, I don't know now. I don't remember if I asked you to install all these packages. If you try to run any individual package here and it says you don't have that package, then you know how to take care of that. It's just a quick install.packages and package name in quotation marks. But you may have all of these. I just want to walk you through a little bit of what each one of these packages are doing in our analysis. So the package, well, tidyverse is is that package of packages, right? Tidyverse basically loads for you, I don't know, 5, 6, 7 different packages that are all part of the Tidyverse, which include ggplot2, includes dplyr, tidyr, things we use every single time. The package car has a ANOVA function we're going to be using, uppercase A ANOVA. There are differences here between what ANOVA function you use and what results you get back. And we'll talk more about it when we get to that point. We're using LME4 to run our model. This is one of the most popular packages in R to run, especially mixed effect model, ANOVA models. If you don't know what a mixed effect model is at this point, don't worry, but that is what this package does. Then we're going to use the package Broom, which is a package that's going to help us to extract the residuals of our models. So if you remember on that formula that we saw, that EIJK at the end, that is the residual of the model. So we're going to be extracting those because all the assumptions of a linear model are based on the residuals of the model. And this is also something we'll talk more later, but sometimes I'm reviewing papers or reading papers where they say, yeah, we check for the raw data normality, and that assumption was met. I haven't really found a paper that backs up you assessing your raw data for assumptions. That is not what we do. We check our model assumptions on the residuals, which is what is basically left of your raw data after you explain everything else with the model. We'll talk more about that when we get to the residual assumptions. Finally, we're going to extract means for the model using the package EMeans, and then do pairwise comparisons using multicomp package. Anyone having any questions or issues with these packages being installed, or maybe having issues with installing them if required?
I have a question,
Yes.
and maybe it doesn't matter, but I think after loading your package, I'm seeing things like attaching core tidyverse packages, all of that. Is it for the installation or just loading the library?
Yeah, so Comfort, this is just the message we get from Tidyverse, and you can see that is not an error, like it's not saying error, it's just like a message, right? So as I was telling you, that Tidyverse is a collection of packages. So when you load Tidyverse, it's actually loading all of these packages here. And it's just telling you if there are any with other packages, right? So it's just a message. And this is something that, you know, is actually, I think it's interesting specifically in our studio. The choice of color for messages, I think, is curious, because we see red and we tend to think, okay, something went wrong, right? We have to check it. But really, that's not the case. It's just, you know, I would only be
The thing is,
in error.
I'm not getting the message.
Oh, you're not getting the message?
Yeah.
So if you run it and you check on your console, is it giving you any errors?
Maybe it's because I'm running everything together. Let me try running it alone.
Yeah, I mean, if you're not getting any errors, I wouldn't worry. Yeah,
Still the same.
yeah, well, that's the same for me. So as I ran the whole chunk, I did not get the message. So I think it's just a behavior, a chunk.
Okay, thank you.
All right. So one thing you're going to notice on this class is if you do the CRD exercise, you're going to notice that we use for the CRD the same data as we're going to use for RCBD, which is going to be the same data we're going to use for split plot, and so on. I made that decision of continue using the same data set so you can see how the analysis would change for the same data sets, right? So you can really focus on the changes on the model and not on data changing. However, this is a big important note, as we already talked about it. You should run the design that you conducted the experiment under, right? So even though we're running the same data set under different designs, you would not do that. You would just run the analysis, the design analysis that represents what you actually did on the field. So this is just a note I want to make here. We're recycling the same data through different models. You would not do that on your side for your own research. This is just for your learning purposes and making easier for you to see the changes in model and not model in data at the same time. All right, so we ran our packages here. We loaded our packages. Next thing is bringing our data. We're gonna, if you come here on this chunk, we're gonna use a function read underscore CSV because this is a CSV file. Open and close quotation marks. You want to navigate to the data folder. So // to get outside of code, hit tab, select data, hit tab again, and it should populate for you that wheat nk bulk.csv. You can go ahead and run that. It's going to pop up on your environment. And then let's take a look at this data set here. All right, so this data set, it's basically a data set represents the same case study we've been checking on the lectures. So we're connecting what we see in the lecture with what we're analyzing in R. So we have 5 columns, 36 rows, where the columns we have here are treatment, so it's just a treatment number. We have wrap, which in this case, wrap is basically a block, and that's the case because this is an RCBD. If this design would have been a CRD, the column could still be called wrap, but you wouldn't say that you have blocks because you really did not have blocks, right? So again, in most designs, we have some level of replication, and in certain designs, that replication equates a block, which in RCBD, that's what it is. We have our nitrogen rate and potassium rate in kilograms per hectare, and then we have our yields. And 36 observations, that's what we've been talking about in lecture. This is how this data looks like. Again, let's do some EDA here. So I think I left you the code already because you're familiar with these functions. So you can just go ahead and run it. We're checking a summary here. So it's really the only variable that could truly have a value that perhaps was not right is yield, because that's what you measured, right? Everything else is basically your design variable, so wrap representing block, experimental design, and then nitrogen and potassium representing your treatment design. So those, should have been correct, and not as prone to typing errors or entering errors. But yeah, so yield here we see that is ranging from about 2,700 kilograms per hectare to about 7,500 kilograms per hectare. It makes sense. This is corn. These values, they're perhaps kind of on the lower side, or I'm sorry, this is actually not corn. I think on my, yeah. So sorry, this is actually a data set that is wheat. So let me just, perhaps this is a difference between what we were talking about in class. I think in lecture, we're talking about corn study. This is data coming from a wheat study. So these values here do make sense for wheat. If you work with wheat, you would, these levels of yield make sense. All right, then let's do a glimpse as well. So if you remember, a glimpse is going to tell you how are those variables being interpreted by R. They're all being considered numerical. And this is a key point that I think you're going to realize with your own data, if you have similar experimental design data, is if you name your blocks 1, 2, 3, 4, which most people do, when you bring that into R is going to look into that column and interpret that as numerical. This is such a simple thing, but it has implications on your analysis, and we're going to see what that is in a second here. Yes, Swabert.
Yeah, I think for my glimpse, I'm seeing them as integers instead of variable.
Which column are you seeing as an integer?
All of them.
All of them.
Yes.
Yeah, I think I'm not sure why the difference, because maybe, I don't know, maybe there is a version of some other packages or maybe of our studio that is not matching between my computer and yours. That is still okay, right? So integer is also a numerical type of variable. So although, I guess it's probably doing that because I don't think there's a decimal point in any of the cells. So it's just assuming as integer because of that, but that shouldn't be an issue.
I think Swabi did read.csv. That's the reason.
Okay. Who made that comment?
I'm Ariful.
Okay, awesome. Thanks, Ariful. Yes. So, okay. So Ariful was saying,
Arif, that's true. That's true.
yeah.
Yeah,
So
I did read .csv.
read.csv is a different, well, it's doing the same thing, but it's from a different package. So maybe that package is treating differently. So let me replicate that just to make sure. Yeah, that's right. Thanks, Ariful. Yeah, I mean, it shouldn't really make a difference when it comes down to the analysis. But if you want to make sure you see what I'm seeing, then use the read_CSV function. You know what? I'm actually looking at this script, and I think I sent you the complete script. Now that I'm looking at it, because there's too much code here going on. Yeah, so, well, we're just gonna go through it as the complete one. So one thing that I wanted to discuss here when we look at this glimpse and we're talking about rep being considered as numerical. So what happens is with every numerical variable that you have in your model, in your ANOVA model, if you give a numerical variable, what any software is going to try to do is going to try to do a regression on that variable. So if I say the block is numerical, it's going to try to calculate an intercept and a slope for block, which does not make sense. That is not what we're trying to do. We could have called these blocks A, B, C, and D, and they would have the same meaning of what we wanted to have. We could have called them, anything else that would not be a number, and they would make sense. It does not mean that block number 2 is 2 times more than block number 1, right? Block, even though we call it numerically, it does not have a numerical meaning in our analysis. So one of the first things we have to do here is to actually transform it to a categorical variable, like nitrogen rate levels, right? So, well, and I guess I just said something else that perhaps doesn't make sense quite yet. So nitrogen and potassium are also being seen as numerical. In our case, we are running an analysis of variance. Analysis of variance, you have your model terms as categorical variables, as factors. So the same way, if we give nitrogen rate and potassium rates, which right now are numerical, to the model is going to try to make a regression. And let me make a quick drawing here just to perhaps help you illustrate this concept a little bit more. So imagine that we have yield on the y-axis. And then we have nitrogen rate on the x-axis. What we want to do is compare means, right? I want to know if the mean yield for nitrogen 100 kilos is greater than the mean yield for nitrogen 0 kilos. I want to know about means. This, when you think about I want to know means, you need to be thinking about ANOVA. ANOVA, your model parameters have to be categorical. However, if you're interested in the overall response, like I want to know how yield changes across different nitrogen rates, not just the ones I applied, but also in the empty spaces in between, that is a regression. The key difference between an ANOVA and a regression is going to be how you treat your explanatory variables, the variables that come after that you explain, yield explained by explanatory variables. So let's say we have here 0, 100. Sorry for my writing not being very clear. And then 200. I'm just going to put a 2 here, and that's going to be enough. All right. So, okay. So the same, and the interesting thing is you could run either an ANOVA or a regression on the same data. It comes down to your goal, your analysis, or your objective of this data. So for example, I have yield as a function of nitrogen, 0, 100, 200. And then I have 4 reps. So I'm going to have a point here. Just imagine these are reps, right? For each one of these nitrogen rates. So let's say that it looked like this. If I am running an ANOVA, my nitrogen rate needs to be categorical. And in that case, what the model does for us is it gives you a mean. It gives you the mean of those values. This is what we're going to get from the model, a mean. If, however, I'm interested on the relationship between nitrogen and yield, and I want to be able to predict values that I did not observe or did not apply on my study as far as nitrogen rates, then you would do a regression and you will look something like this. So for a regression, the model is calculating your intercept and your slope. It's not calculating means. If you do regression, the model gives you intercept and slope. If you do ANOVA, the model gives you means. In our case here, the difference between running a regression or an analysis of variance is to make sure that our explanatory variables, in this case, your nitrogen, is coded as categorical. Right now, R is interpreting that as numerical. So we have to fix that before we get into the model. So the way that we're fixing it, I left the code here. I think even though I'm giving you the whole code, but I think you can still understand what is going on without having you to type everything. So we're starting with RCBDDF using a pipe. We're getting into a mutate, and I basically want to overwrite the columns rep and rate and potassium rate with the function factor. So this function here basically takes what is inside of it. So I'm taking the factor of rep and factor of nitrogen and potassium and just overriding that on the current columns, rep and rate, potassium rates. And then finally, after that, I have another mutate where I'm creating a column called treatment name. So I don't have this column yet, but this is just a column that is combining nitrogen rate and potassium rate with a plus in between. And whenever we want to do that, we need to use this function paste 0 for that. So let's just run this chunk here and print it. So we still have 36 rows as you would expect. Now look at how my rep is FCTR, stands for factor. My nitrogen rate is a factor. My potassium rate is a factor. My yield is still numerical. It has to be numerical in this case, right? We don't want to have a factor of yield. Don't want that to be categorical. And then we have this new column for treatment name, which I'm basically taking the value that's under the nitrogen rate, adding a plus, and the value under the potassium rate. So then we can explain this. We can use this column in the plots if needed. I do want to take a quick moment here and just, since I made a mistake of sending you the complete script, even though I thought it was the partial, so you have the full code already. But if you would be interested in learning exactly what each function of this flow, this pipe flow is doing, what you could do is basically just stop the flow of the pipe with a comment and then run. So it basically stops right before that pipe. So then you print it, you see what it did. In this case, it didn't do anything because it's just the same data set as we started. Let the pipe flow and then stop the next pipe, run it again, and then you can print it and see what happened. Basically, we just transform into factor. We see that effect taking place. And then finally, if you let it go through the end, you just get that treatment name column that is just combining with the paste 0 function, combining the nitrogen rate and the potassium rate into a single name. Question?
Yeah, so even when you remove the pipe, you don't have to include like the object name in the function anymore. Because I know like before we learned about the pipe, we were including like the object name in every function we're doing actually like, okay, but even now you don't think with that object name.
Yeah, so Zach is asking about not including or not creating object names in between. So when we went through the data wrangling exercise, let's say this step would have been saved as an object, and then this object would then be fed into the next function and so on, right? In this case here, because we're using the pipe, we're actually not creating all those intermediary steps or objects, right? We're still doing all the steps, but then we're assigning the entire result to one object, which is this on top, right? And so if you remember, one of the differences is if you use the pipe, then the pipe takes everything on its left and feeds that as the input of the function to the right. And perhaps this is a good place to also explain the following. This is actually a good, test question to ask you all that I haven't done in the past. So the concept of the pipe is take what is on its left and feed that as the input of what is on its right. For this first pipe here, I think is pretty straightforward. That is taking this data set and feeding that as the input of this mutate. Now, for this pipe, this second pipe here, what is the incoming data set? Is it just this? Or is it the whole?
Both, result of both.
Yes, right? So each pipe on any pipe flow is going to take everything before it as the input of the next function, not just the immediate next function as the input. Everything before that pipe goes into the next function. So that's a good concept too. In a way that, sometimes I write like a complex pipe flow that when I was thinking about it and thinking of the steps I have to do, I'm like, okay, I have to filter here, select there, mutate here, change this, pivot right, or do this and that. And it's working well. But then sometimes I come back to the code and I'm like, why did I do this step here? Why was that a required step? And I want to kind of think through what I thought initially. One simple way is, again, you can come and comment off that pipe, run it and see how it looks like. It kind of puts you in that state of like, okay, this is what I had when I thought of this next step. So maybe that, that sometimes helps me to understand why I did something, or even if you get an error, like if you're running a pipe that used to work and now doesn't work for some reason, and it's like a 100-line code pipe flow that has a lot of stuff going on. You don't know where is the error. What I do to troubleshoot is I come here, I block the first pipe and I run. Did it work? Okay, so the error is not here. I let it flow until the next pipe and run. Did it run? Okay, so the error is not here. Until you find what function is giving you the error, then can help you to troubleshoot that way as well. Awesome. Okay, so now we fixed our, and again, this is such a small thing, but it's such an important thing because again, if you're running analysis of variance, most likely your explanatory variables, which is what goes on the right side of that y equals x, explanatory variable is your x. It's all the variables after the equal sign of that equation. Those variables on an ANOVA analysis of variance analysis, most of the time are categorical, or in our language, a factor. They should be treated as a factor. And normally, again, for block and also for nitrogen and potassium rate in this case, because those are numbers, when you bring into R will always interpret that as numerical. You have to force R to know that it's not numerical, it's a categorical variable, a factor variable, before you can model correctly. Otherwise, your degrees of freedom are going to be off. I mean, the whole thing is not gonna be what you're expecting. And so that is a simple yet important step. So go ahead and run that RCBD. So we have RCBD DFW. The W means wrangled. I always like to do that. I would discourage you to import a data frame with a given name, and then you wrangle it and assign it to the same name, because then it's going to be harder for you to know, am I working with the raw version? Am I working with the wrangle version? So I always add a W after wrangling something, so I know this is the wrangle version. All right, so now if you ask for a summary of it, if you just run that chunk, one of the things you're going to notice is that before the summary function, before we wrangled it, the summary function was seeing RAP and rate and potassium rate as numerical. And if we go back to that chunk, it was giving us a statistical summary for it, right? So every time R sees a column as numerical, it gives you a statistical summary of that column. Now that we force those variables to be categorical or a factor, now it's not giving us a statistical summary anymore. It's just giving this information of how many rows it has for each one of those levels. So this is what we would expect. We know that we have 4 applications. We have a total of 9 treatments. So 3 nitrogen rates, 3 potassium rates, and all combinations of them for a total of 36 rows, 36 true replicate information, right? 36 degrees of freedom we're going to have in our analysis. And then just a quick summary of yield and how that is varying. Okay, let me take a look at this code here. And before I walk through this, I do want to, yeah, I mean, when I give you all the code, it's harder for me to ask you without you having the chance of looking to the answer actually. But I just want to show you what I'm doing here. So EDA plots, in this case, we're interested on means. When I'm interested on mean, normally I would try to look at a box plot, right? So a box plot is going to give you some information of a distribution of the data according to something. So for now, I just want to comment off this color and just break the line here. So the parentheses and the plus continuous is just the color equals nitrogen rates that is not appearing. If we just run until here, so we put nitrogen rate on the X and yield on the Y. If we just run this, we just get that canvas, right? Until this point, I have not asked for a geom. Now, if I let it go until geom box plots, it's gonna give us these 3 box plots for nitrogen. This is also something interesting for you to notice. If we had not changed nitrogen rates from numerical to factor, if nitrogen rate was still numerical, when you do this, R would just give you 1 big box plot. So you don't have to make the change I'm going to do here. I'm just going to show you. So RCBD DF was before we wrangled, right? So in that case, N rate is still numerical. If I run this with a box plot, it's going to give us 1 big box plot because it thinks N rate is numerical. So if you ever see something like this, you were expecting 3 box plots and you see 1, maybe that's the reason. Most likely that's the reason. So I'm going to come back here and re-add the right data frame, so the DFW, where ggplot is giving you 3 box plots because it's looking at nitrogen rates and understands that that is a factor, is a categorical variable, and giving you this distribution here. All right, so you could, I'm going to actually make a quick change here from the code that you have, which is, so the box plot, if you're not familiar with box plot, again, this is a very basic stats concept. Please look into it and get some idea of what that is. But just a quick summary is the box plot takes all the data points related to that box plot, so just the 4 reps on the 0 nitrogen rates, and it shows you this box with some whiskers and some points. The main thing for you to know is that this line, the black line in the middle of the box, in ggplot represents the median, not the mean. So the median of that, the bottom edge of this box is the 25th quantile. The top edge of the box is the 75th quantile. The box size is the inner quantile range. The whiskers extend, I think there's a formula there, but I think it's like 1.5 times your 75th quantile and 1.5 times your 25th quantile in different directions. And then points are shown whenever you have any data point that extends beyond the value of the whisker. So this is a quick way for us to look into a data distribution. It's one of the ways. There are other ways to also do this. I like box plots, but there are other ways as well. So what happens is behind each one of these box plots, they were made based from 4 points, or actually in this specific case, more than that. 4 reps times 3. Yeah, so each one of these box plots has 12 data points because it is coming from 4 reps, but also you have all the potassium data in there as well. So if I wanted to see the actual points, I could add a geom underscore point. And I'm not going to add a plus quite yet, just stop at that geom point. You would see all the actual points that were used behind the scenes to create those box plots. Now, on my initial code here where I had a geom jitter. So jitter is basically a geom point that adds some jitter to the points to make him, if you have a lot of points that are right on top of each other, you're not seeing that you have 2 points because they're right on top of each other. Jitter makes them a little bit offset in a random fashion, so you can see more of that data in different ways. So I'm going to remove the geom point, just let it run through the geom jitter and the theme that I'm just changing something there. So geom jitter just adds that jitteriness to your data points in case they're overlapping, and so this way you can see them better. And then if we come back here and just let the color equals n rate go, or remove that comment, it's going to let it through, and is basically just going to add a color to each one of the nitrogen rates. That's what we're asking. And because initially, if you don't let the theme function go through, if you just run like this, so if you stop that ggplot right there, it's going to give you a legend, as we know, because color equals nitrogen rate is inside AES. Remember this is a key thing when you're thinking about your data. If you want to map color, in this case, to a column, it has to be inside AES. Then it gives you a legend. In this case here, I already know the nitrogen rate is 0, 100, and 200. So this legend is kind of not necessary. So I just removed the legend by using this function called theme, and the argument legend position equals none. That is one of the ways you can inhibit a legend in ggplots. All right, so the goal of EDA is you looking at your data, and even though you already have your hypothesis, already have your objectives, but EDA kind of gives you a chance of perhaps making a bet with yourself and thinking, I thought initially that I would have a nitrogen effect. At least looking at this data, I don't know if it's significant. I don't know if we do have a nitrogen effect on this data set, at least. Right? So this is the goal of that EDA, is give you an opportunity to look at your data and try to understand what is going on. All right, so the next piece of code is basically the same, but with potassium instead of nitrogen. So now potassium rate is on the x-axis, potassium rate is the color, and everything else is the same. So we can go ahead and run it, and we can look into those box plots. Okay, so our hypothesis coming in was that we would have a nitrogen effect and a potassium effect on yield, in this case, wheat yield. What do you think? What would you say about what we're seeing here? Micah, what do you think? Do you think, I mean, just from, of course, we are not making statistical inference yet because we have not run a model. It's just, from what you're seeing visually, would you say we have a potassium effect on yield?
Outliers, also there may be a very slight.
Yeah, so perhaps there is, but there is a lot of noise, right? At least looking at this box plot, at least it looks like there's a lot of noise. Yeah, I don't know. I mean, however, if you remember, one of our hypotheses was that perhaps there is an interaction between them. So let me just take a quick look here on the next code. You know what? I think this code here, I would really, even though you already have it, if you don't want to delete it, you don't have to. But I think it's going to be helpful for your own learning if you just delete at least parts of it. So maybe delete that facet grid. Just delete that for a moment. So where is that facet grid? Because that's a really nice concept in ggplots that, although in this case, it's going to help us a little bit, but it can really be very helpful if you're making many plots, all on the same, based on the same data sets. All right, so the main effects, when I say main effects, I mean the effect of potassium by itself, the effect of nitrogen by itself, they really don't seem like they're really strong, right? When we look at these box plots, at least. Now, I want you to, even if you have already run this next chunk here with the previous function, I want to ask you, how could you show nitrogen and potassium interaction in a plot? There may be a few different ways that we could do this, so there's no right or wrong answer, but yeah, I'll just leave it at that. Like if you, based on what you know in ggplot, and forget about that facet grid function that was there, assuming you did not know about that function until this point, how do you think we could show nitrogen and potassium rate effect on yield in a plot?
Can I answer?
Yes, go ahead.
So one way would be to do a line chart where we would see if the lines intersect or not. So if the lines are intersecting, maybe we can deduce that there might be an interaction. If the lines are parallel, then that would indicate there's no interaction.
Okay, so Shakir, but then what would be, so let's say you have a data, I mean, I can visualize what you're saying, but I'm trying to think like, I think for us to do that, we would have to do some extra wrangling first, so we could have a way to do that, or maybe, yeah, I think we would have to do some wrangling to be able to successfully do that, right? So that is possible, but we would need to do a little bit more work behind the scenes to get to that point. So without doing that work, or perhaps not going that route specifically, but perhaps if you think about, I mean, really, so here's something we could try. So we have right now on this code here that I asked you to delete that facet grid, we have nitrogen rate on the x-axis, and we have the color being potassium rate, or sorry, the color being nitrogen rate, right? Another thing that we could do actually in this data set that is not what I was originally going to show you, if you print this data set, which column do you think we could use to show all of those treatment combinations? Treatment name, right? So we have one column, one variable that represents that combination of nitrogen and potassium. And that's really one of the reasons why I created this column, was so we can use it afterwards. So if instead of having X equals nitrogen and color equals nitrogen, if you change that to treatment name, that would be one way. Okay. However, so this would work. And so, Shakir, one of the reasons why I'm not showing a line is maybe the line would work if we had already calculated the means. Because then you have one mean for one treatment, and one mean for the other, one mean for the other. Without the mean, we still have all the replications there. And I think that if we make a line, it's not really gonna know which points it should connect. It's gonna be like a jigsaw line, because it's not gonna know which point should be connected to which because of the reps. But yeah, but that could still be an option. All right, so we saw how if you have a column that has all the combinations that you need, you could use that. There is another way, which was the original way I wanted to show you. So I'm just gonna do a Command Z to undo here and have nitrogen rates still on the X and on the color. But there's a function, there's a family of functions called facet underscore. So right after that geom jitter, let's go ahead and say facet underscore, and then you see there is a grid, there is null, and there is rep. There's some differences to those, but we're gonna try grid first. So what facet grid does is we're gonna specify one column name inside of this facet grid. Is going to look into that column and is going to look for how many levels that column has. That column for us is going to be potassium rates. So it's going to go under potassium rates and see there's a 0, 30, and 60. For each set All the data in our data set where potassium rate is equal to 0 is going to have its own plots. All the data the potassium rate is equal to 30 is going to have its own plots. And the same thing for 60. So is named facets because it's making different facets as many as there are levels under the column that you specify. So if you come here and you do dot tilde K rate underscore kilograms per hectare, this is what you should see. So again, it looked at the column that we specified, potassium rate. It checked how many levels it had. So it had 0, 30, and 60, and created a facet for each one of those levels. Yes?
Why do we do the dot and the tilde?
Yes, great question. Okay. So Jonathan's asking, why do we do the dot and the tilde? So this function specifically, facet grid, allows you to give a column before the tilde that it goes on the rows, a column after the tilde that goes on the columns. So let's say if instead of doing dot tilde potassium rate, if we had done potassium rate tilde dot, it would make this vertical. This becomes even more helpful if your data has more variables that can help you explain. So let's say if we had location, if we had, so 36 times 2, because we had 2 locations, we would have twice as many rows. You could do a facet grid where potassium rate was in one side and location was on the other side. So basically you would have a matrix of plots where on the rows you had different potassium rates, on the columns you have 2 locations. Even though in our case, you may think, I mean, okay, I could have maybe done a filter, potassium rate equals 0, and do a plot and do 3 different plots, one each chunk. You could have done that, of course, you could have. This function becomes really helpful when you have many levels under that facet column. One example is during my PhD, I was working with this long-term study that we had 25 years of the same study being conducted on the same place. So and it was an nitrogen rate study as well. So imagine something similar to this, but I had 25 years. I wanted to see that response over 25 years for each one of the years. I could have done 25 plots by hand, or by hand, not hand, but different chunks, right? But then I just came here and I said year, boom, I had 25 plots. Of course, in this case, it doesn't work, right? Because we don't have a column year in this case. But for me, it worked. Putting year on the facet grid gave me 25 plots that all looked the same, had the same scale, same color, same legend, everything the same. So it's a really powerful plotting function for you if you have columns that you want to facet by. All right, so I'm just going to come back here to what it was before. So we had a dot tilde potassium rate, right? All right, so now that we made that plot, interesting, right? Now it's kind of a different story than looking at just potassium alone or just nitrogen alone. It seems like there's something going on here, right? So I want to ask maybe somebody online to just, help me to get started. How would you interpret this? Like, what are you seeing here? Let's see, Priscilla, what do you think?
It's hard to say for me just by looking at the plot map. It's easier for me whenever I look at the statistical model, whenever I run it. But if I had to say something,
Well, let me start by asking you this. I think we kind of agreed that looking by the effect of potassium by itself and nitrogen by itself didn't really seem like there was a lot of effect, right? But we're still going to test
yeah.
it, but visually didn't seem like there was a lot there. Now, what we're doing here is one of the ways to look into that interaction, right? So we're plotting nitrogen on X, and then each plot here is a different potassium rate. So based on what you're seeing, do you think that, at least visually, would you hypothesize that there is an interaction between nitrogen and potassium?
Yes.
It looks like, right?
Yeah.
Yeah, I agree. And then Priscilla, I do want to use your comment to also make a connecting point here. So on my research, when I make figures, when I publish things on presentations, whatever it is, I try my best to include raw data, which is what this is, and a statistical summary, like a letter comparison, letter separation. The reason for that is because a lot of times people would just show you, for example, a bar plot with a mean. I mean, that is, it has some information to it, but it's really not the most useful plot as it could have been. So imagine if instead of showing you, so imagine that the median, so the box plot is showing the median, but let's just assume it was the mean coming from a model. And imagine that I will show you just a bar stopping at the top of where the solid line of the box plot is. I'm showing you a mean, and that's it. You really don't have an appreciate, or you don't allow your audience to appreciate the variability around that mean, even with the raw data, right? So every time I can, I try to include raw data so people understand the variability of that raw data. And then on top of that, bring a statistical summary that would be that ladder separation that we're going to be doing in the end, right? So Priscilla, from what you're saying, and this is just a spoiler perhaps, when we get to the end of this exercise, we're basically going to be doing the same plots. The difference is going to be we're going to have letters on these box plots to help us to interpret if that difference is statistically significant or not. But the plot is still going to be the same. So I do want you all to think about this as far as, you know, I mean, of course, right now we don't have that statistical model comparison yet to really be able to tell statistically if these box plots are different or not. But at least by looking at them, we should be able to come up with perhaps some idea of this, of if these are different or not. Okay, so yeah, so I think, you know, looking to this. Well, let me ask somebody else maybe here in Athens that hasn't helped today yet. Charishma, what do you think? What would you, so we're kind of thinking that we have an interaction here between nitrogen and potassium. Why do you think that is? Like if you were to interpret this plot and say, well, I think we have an interaction because here we see this and there we see that. Madhuparna, what do you think? Yeah. Well, let's see. Aitan, what do you think? All right. The guys are like itching. Ruben, what do you think?
For me, in my case, for kind of probably I'm not analyzing the whole graph, but I'm analyzing the extreme that is like 60 of potassium and then the nitrogen rate.
Mm-hmm.
And if, for example, we see that we don't have nitrogen, we see the yield increasing for potassium. So it's like the more nitrogen, the less, like they are inverse.
Mm-hmm. Yeah. So if we did not have an interaction, maybe we would see like under the first panel, we would see the same pattern of box plots. On the second panel, the same pattern. On the third panel, the same pattern. It's not what we're seeing here, right? We're seeing different patterns of nitrogen depending on the potassium rate. This is one indication that perhaps there is an interaction here. All right. So if you, especially for example, if you compare, all three potassium rates have different nitrogen responses. So the first one is like you decrease yield with a little bit of nitrogen, and then you increase back up with a lot of nitrogen. On the second potassium rate, we start off with the least yield with 0 nitrogen, and then you increase yield and kind of looks like remain the same between 100 and 200 kilos of nitrogen. And then when you apply the highest potassium rate, you're actually losing yield as you increase nitrogen rates, right? So this is how, at least this is how I would interpret this. And I do encourage you to think about these because you probably have even more complex designs and data than this. So you having the capacity of looking at this and even just trying to go through what you're seeing is important. Another way we could look into this as well is if we just compare the zero nitrogens across different potassiums. So just look at the red box plots. So zero nitrogen with zero potassium, this is the yield. Zero nitrogen with 30 potassium, we decrease yield and then we increase afterwards, right? So even just, there are different ways of looking at an interaction. This is one of them, or these are two ways, I guess. One is looking at what we're seeing inside each one of the panels, and the other one would be looking across panels as well. Yes, Omar.
Sorry, Professor, I just wanted to mention that it's time for the class.
Yes. Thanks, Umar. And I have to change this. So the computer right in front of me is 11:30, and on my computer I see it's 11:35. So I apologize for that, to be holding you. So let me get your attendance, and then we'll continue from the next class. Is it open already? Okay. So I'm already open the issue for attendance for today. Please go ahead and claim your attendance. Yes.
Wanted to ask something, like, I don't know if it's for me because the data points in my box plot, they appear to be mirrored for some reason. I don't know why. Like,
Mirrored. So let me just do this. I don't want to keep anyone else. So if you claim your attendance and if you need to go, you want to go, you're free to do that. I'm going to stay for a little longer here just to ask or help with any questions. Just gonna stop recording.
Dr. Bestos,
Yes.
can I ask a question?
Sure. Just stop recording here.